everybody. Yes, I'm here. I'm right here. Hello everyone. Very good evening and a warm welcome to Vedantu Enlite. This is your master teacher Nabamita Mam, and today we are here with yet another brand new chapter and we're going to complete it today itself, and that is DNF block one shot. Okay, yes, after that we will be doing S block, and then I think we are done with all the blocks of the periodic table, isn't it? So what's up? Yes, from the last 15 minutes, what happened to you? Hi Santosh, hi Harini, hello Varshini, hello, I'm here, I'm so sorry, I'm just 1 minute late. I had to just, quickly run to the washroom and fill up my water bottle and come here. I wanted to drink some water as well. Gala sukh gaya, like I have been talking for the last 3 hours just like that non-stop. So yes. Hello everybody, all cricket highlights, Mahadev Sadbhai. Oh my god, amazing. Finally seeing so many students. Do call up your friends quickly so that we can start and nobody is missing out on it, and you know that more the merrier always, right? The more number of students get to watch it, I also feel happy, and I'm sure that most of the students, they get to benefit, isn't it? Thank you, Isaac. Hi, Nishant. Hi, Nandini. Hello. Last session was awesome. Thank you so much. If you like it, don't forget to hit the like button so that the more number of students hit the like button, then we understand what kind of session should we bring you, isn't it? Yes. Excited, everybody? Okay, so shall we begin, everyone? Shall we begin? Looking different. Yeah, I got a haircut. I don't know if you observed it. I got a haircut. Yes, I got a haircut. Very, I think yesterday only I got a haircut. Yeah. Got a haircut yesterday. Hello Pilot, how are you? Optimal learning with VR. Now are you going to do this only every session? Do you remember me? Do you think I'm Amir Khan from the Ghajini movie? That every 15 minutes I forget things, huh? I don't. I do remember you. I know you have asked me that question that you asked me, ma'am. I dare you, which college you belong to, right? That's you, isn't it? Yeah. So I do remember you. Thank you so much, Nandini. VS, my name is Nabamita Bhattacharjee, okay? Nabamita Bhattacharjee. If you find it too hard, you can call me Nobita, because that's what most of the students, do call me. No, we will be finishing it today only, okay? We will be finishing it today only. Yes. Start. Yes, Bhargav, I can't understand whatever you have written, but yeah, let's begin. Okay. So, by the way, I hope that you all know about this Children's Day, or this whole week we are celebrating what? We are celebrating Vedantu Online Child Safety Week, and there have been a lot of sessions that were taken by Vani ma'am, that were taken by Abhishek sir, that were taken by Tarun Sharma sir. Please do watch them to understand what all of that is there. No, it's fine, optimal learning, it's okay. Without P block, can I able to understand D block? Ranjita, why did you not understand P block? I've actually already completed P block, and now I'm moving to DNF block. P block is done. Coordination compound is done. P block is done. I have taken care of what? Periodic table, periodic exceptions as well. Woo! Which world are you in? I know I'm new to this channel, but I've already completed so many chapters. I think you should go back and watch it, my dear student. Please watch it. Only then you will be able to understand. Thank you, Nadesh. Thank you. We will have Menti today now. What? You are in 11th and 12th. What will you do with Menti? Menti some other day, okay? Chalo, where are you from? I am a Bengali, sweetheart. I am from West Bengal, but I've never stayed there because my father had a transferable job, so we kept roaming around. Anyway, enough about me. Let's come back here. Focus up. No, it's okay. Optimal learning. I have forgiven you. How can I not forgive you? I have forgiven you. Exam date of May is that when they announce, then we will tell you, okay? Okay, guys, I need you all to focus up. Everybody, are we all ready with DNF block? And also, can I please expect you all to sit with a copy and a pen, please, because it's going to be very important if you make notes while I'm teaching you. Otherwise, everything goes poof out of your mind, okay? So let's do that. You got a physics exam, no problem, but watch this session later, okay, so that you don't miss out on it. Okay. Now everybody, we all know already that this is the long form of modern periodic table, isn't it? Do we not know this? We already know this. Where is the pen? There is no pen. I don't see the pen. Alright, I think I'll write with this. Oh no, I found it. Yeah, the session has just started, Lama. The session has just started. Yeah. So we all know that this is the long form of periodic table, isn't it? Now, periodic table obviously had been through some changes. This is not exactly how it looked like from the beginning, correct? We all know about this. Now, when we come to the long form of periodic table, you all know that this is your P block, isn't it? This is your S block. Yeah, this is your P block. And here comes your D block, and this is your F block. Now, you can see the F block are those ones who are already out of the periodic. already out of the periodic table. They are not really considered in the periodic table. They are outside, isn't it? They are outside. Now, yes, Dobonese, triads and all of these, there was a cyclic and all of that we have learnt about, isn't it? The voice is a little bit low, is it? Okay, now, what about now? Thank you, Chinmay, thank you so much. Yeah. Okay, is it fine now? Okay, I'll try to stand here and talk, okay? So this is your D block. Now, do you know that the D block is also called as transition elements, isn't it? What is it called as? It is also called as transition elements. Now, why is it called as transition elements? Do you know? Anybody knows? Yes, it is called as transition elements because this block right here, what does it do? It changes the property from S to P. The changes in the properties that is seen in S and P, it happens through this. So, this is the transition elements. Now, you can see that this F block, it is already outside, right? It is not in the, change the color pen also. Alright, okay. Okay, yeah. Wait a second. What color should I keep? What color should I keep? Black will do? Black will do? Is this better? This is better? Or you are not able to see? Yes, so these are called as inner transition, okay? The F block elements are called as inner transition elements. Are you understanding? Are you understanding? We will be doing PYQs later, not in this session, in the next session, okay, Bhargav? We will do this in the next session. Today we are only doing one shot. We will just see, you are still not able to see, yeah? Okay. Alright. How do I change the... I think... Now is it fine? I can't write now. Okay, something weird happened. I don't know, for some odd reason it is very, this thing. It's very thin today, okay? I can't increase the thickness. I was trying that only, but I'm not able to increase the thickness of the pen. It's sad. Why is this happening? I don't know. Not happening, guys. Acha, chalo, we will see later, yeah? Let's not. I have changed, yeah. I've kept it as black also. I've kept it at red also. Nothing is happening. I'll try to write bigger, okay? I'll try to write it bigger, okay? I will try to write it bigger. I'll try to write it bigger, okay? Is this better? I'll write it like this. This is fine. This is fine. Just adjust for today, no? Just adjust for today. I anyway got really late today for the class as well. Chalo, theek hai? Haan. Now can you all see? Now can you all see? D is transition. D is transition, this is fine. I am writing. let's not worry about it. I'll give you the notes, don't worry, okay? Let's just listen to me, okay? Yeah. Tanush, forget it. I'm kind of tech challenged. I will not be able to solve all of these. Yeah, so let's just be with me. Yeah, please just be with me, okay? Yeah, so as I was telling you, this is called as transition metal because from S to P, you know, the properties change. So this is your transition metal. Now we see that the F block elements are already outside, right? This was one of the disadvantage of the modern periodic table, that the F block elements, they still did not get their places in the periodic table. They are outside. So they are called as inner transition elements. Okay, they are called as inner transition elements. Now there are few things that you will have to remember. There is no other way. How much ever I try to make it easy for you, I will not be able to do anything, but you will have to remember it. Okay, so what are the things that you have to remember it? Can you all see here that the D block elements, it starts from this 3D, okay? This is the 3D, okay? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, okay? These are your 3D series, everybody, okay? This is your 3D series. Now, we have learnt about this even in the periodic properties. We have learnt about this even in the coordination compounds. So, by now, I'm hoping that you all already remember this, isn't it? So, the first one, this is your 3D series, this is is 4D, this is 5D, and this is 6D. Okay. Now one thing, listen to me very carefully. This 6D series, okay, the 6D, okay, the 6D, remember it very carefully. This is incomplete. This is incomplete. We still haven't been able to find all the elements here, okay. All the elements are not found here. So 6D is called as the incomplete series, okay. Next lecture, NEET motivation Tamil. Focus here now. Focus in this class first, okay. Alright, focus in this class first. Although we do have names, right, we do have names, but 6D is called as the incomplete series, okay. But in the 5D, what will you find in the 5D and the 6D? Guys, 6D, Varshini, 6D. What is this? See? 3D, 4D, 5D, 6D, okay? 3D, 4D, 5D, 6D. It's 60, okay? Now, moving on everyone, listen to me very carefully. Please focus up, yeah? No other chat and all here and there, okay? No other chat and all. DNF block is also, I mean it's easy, but if you listen to me, it is easy, okay? Yeah. Okay, now in the 5D, you will find the lanthanoids, okay? And in the 6D, you will find the actinoids, alright? It's the lanthanoids and the actinoids that you will find here, okay? Now, so this one, scandium you have learned, okay? Scandium you have learned. Now one more thing everybody, one more thing that is very important is the transition elements, no? The definition of the transition elements, if you read, you will find that it is said that they always have impartially filled d orbitals. Are you listening to me? What is it said? It is said that they always have partially d orbitals filled, okay? Partially filled d orbitals. Basically, it means that it's incomplete. It can be D1, it can be D2, it can be D3, D4, D5, D6, D7, D8, D9. But D10, that means it is fully filled, right? D10 will be fully filled, isn't it, my dear student? Now tell me something. Everybody. Using the same definition, can we say that zinc, cadmium and mercury are not your transition elements? Can we say that? Zinc, cadmium and mercury are not transition elements? Yes, they are d block elements, but they are not transition elements because they have filled. Yes, their d orbital is completely filled. Yes. So remember this everyone, this may come in your board exam, that zinc, cadmium and mercury, they have D10. So their orbitals are fully filled, okay? Their orbitals are fully filled. Are you understanding? Is this clear everybody? Okay, is this clear? Now remember few things, that the 3D series from scandium to zinc, it is 21 to 30, 10 elements, okay? 10 elements. First one has 10 elements, the second one from yttrium to cadmium, again 10 elements, but here my dear student, do you see there is a lag here, there is a gap here? Everybody, 57, it starts from lanthanum 57 and then hafnium, it's 72. It is 72. Harshit, no. Harshit Sahu, what about zinc plus? What am I telling you is that the definition says that even in its oxidation state or not about, we are not talking about oxidation state. We are saying that it should have partially filled d orbitals. Okay, partially filled d orbitals in its ground state. Not talking about the oxidation state. We're not talking about the excited state at all. We're only talking about ground state. Okay, Harshit? And that is why zinc, cadmium and mercury will not be considered as transition element. But yes, they are they belong to the D block obviously. Got it? Anuradha, CFT, crystal field theory. That we did it in this thing, my dear student, coordination compound. Can you please go check it out? I think you'll find it there. Okay? I think you'll find it there. Yeah, now here, coming back, everybody focus up. Anuradha, I just told you, my dear student, CFT is crystal field theory. We read it in coordination compounds and I have already taught you that. Okay? Yeah, coming back to it, everybody. Now from 57, you will see a gap here. Hafnium is 72. Why? Because here you have these elements. What do you have? You have lanthanum, cerium and all of that name, right? All of that name that you will find. These are all your F block and they are inside here. Now if you put them inside here, you will see that the whole periodic table, how beautiful it looks, it will not look any it will not look any longer beautiful because the whole shape will be disrupted, right? The whole shape will be disrupted. Are you getting it? Yes. So here you see a gap here from 57 it directly jumps to 72, okay. And the same thing here happens here as well. You will see that 89 from 89 is your actinium. From actinium to directly jumps to 104, that is rutherfordium. Are we clear with this, everybody? Is this clear? These are our elements, okay. These are our elements. Now everyone, let's talk about something. So what do we have? We have 21 here. Scandium is 21. So how will we write its electronic configuration? We know that the last shell will have 3d14s2. Titanium 3d24s2. Vanadium 3d34s2. Chromium, what will it be? Chromium will be what? Yes. Come on everybody. What will be the electronic configuration of last valence shell? Chromium. Tell me. Let's see everyone. Yes, what is it? 3d14s2, 3d24s2, 3d34s2. This should be 3d44s2, but instead everyone, is this 3d4 and 4s2? No, 3d5-4s2, okay. 3d5-4s, sorry, 4s2, no, 4s1. So remember, everybody is asking me, ma'am, should we remember it? It is very easy to remember. Just remember that chromium, right here, chromium, and then again, sorry, copper. These two have a different valence electrons, okay. These two only have difference. But otherwise, all of them, say 3d14s2, 3d24s2, 3d34s2, okay. Then again here you will find 3d54s2, 3d64s2, 3d74s2, 3d84s2, okay. And then this will be 3d94s2, but no, what do we see? We see 3d10-4s1, and then again 3d10-4s2. That's it. And we know that the half-filled one is more stable. That is what we get to see here, okay. And the same thing we get to see in copper as well. But of course, manganese and zinc also we get to see. But in chromium and copper, we see a different kind of orbital. We see a different kind of electrons, right? Everywhere it is 4s2. So coming back to the general electronic configuration, what will be the general electronic configuration? Can I see it in the chat box, everyone? What is the general electronic configuration? Tell me. Let's see. What is the general electronic configuration? Come on, of D block. D block, come on. Yes. What is the general electronic configuration? Tell me. General electronic configuration of D block. Any idea? ND. Harshit, you almost got it. Very good. Empzane. Very good. It is N-1, guys. It is N-1. Okay. It is N-1. D1 to 10 and NS2. Okay. See. It is 1, 2, 3, 4. Okay. It should be 4. But 4 you get here. Okay. 4S2. But this is N-1. So you write 3D. Okay. That is why we call it. Somebody asked me, ma'am, is it 6D or 7D? We see N-1D. No, that's why 3D, 4D, 5D, 6D. Got it? Got it, everybody? Very sorry, Suchi. Sorry. Sorry if I missed out your name. Okay. So do we understand this much clearly, everyone? Yes, it is N-1D, 1 to 10, NS2. Now we will talk about the exceptions also. Now tell me something. Why do we see exceptions here? We saw exceptions in S block. We do see exceptions in S block. We do see exceptions in P block. But here the exceptions are more. It feels like we're not only studying the concept, but we are only talking about exceptions. Why? Why is it exceptions? Why does it have so many exceptions? Can you even think about it? I'm pretty sure that you know it. Anuradha, please focus up. No, I understand your JEE exam must have been announced, but how will you prepare for the exam if you're not studying? What will you do with knowing the dates only? Yeah, you have to study also, no? You have to prepare also, right? So I'm trying to help you with your preparation. So please prepare now, okay? Hari Prasad, when will you start metallurgy? Sweetheart, are you an astrologer? This is something that I ask all my students. Yeah, why do you want to live in this thing? Why do you want to live in the future? Huh? Live in the present. I'm teaching you D and F right now. So focus up here. You will learn about all the other things later. Varshini, all of that you're going too deep. You know what? I'll tell you what. I'll tell you. These transition metals, no? Why do they have so many exceptions? Is because the fact is that the gaps between the energy, right? D and S. D and S. Obviously, it should have been D, right? Or it should have been S. But then the D says that I'm right here. So what happens, you know, you must have seen those like in different coaching institutes, or maybe even in lot of, you know, this coaching institutes, you know, they have something called as A batch. There's something called as A batch. In A batch, everybody is topper. In A batch, everyone is a topper. So if the first topper is not studying for 1 week, the second topper would already, you know, the second topper will be like, don't study, I'm right here. Right? The second topper is right there. Maybe because of 0.5 marks, he is the second topper. Correct? Have you seen that? Have you seen that in coaching institutes? You have these kind of classes where the A batch, everyone is supposed to, you know, crack JEE, everyone is supposed to crack NEET. Have you seen that? Exactly. So kind of like this here also, what happens? The gap between the orbitals is not so much. The energy gap is not so much, right? The energy gap is not so much. So the moment the valence shell is like, I am the valence shell, the second one is like, you really think I'm also right here? They are also going to say that, no, I'm right here. I'm going to help you. No, you're not the valence shell. I'm right here. I'm just here. What do you think? So what, you are at the last. So this happens kind of, you know, this kind of happens. So they because of this, the electrons can jump very easily, right? The electrons can jump very easily. And because of that, you see so many exceptions. And sometimes what happens, not because of one electron, sometimes what happens, 2 electrons jump, or sometimes only 1 electron jumps, right? So because of this, you get to see a lot of exceptions, you get to see a lot of bonding. Yes, there are more electrons who are available for bonding, and that is why this whole chapter is there. Okay, that is why the whole chapter is there. I'll tell you how to remember oxidation state. It's very easy, don't worry. Now we go to general properties. Shall we, everyone? Let's run. Yes. After speed up. I am explaining the inorganic chemistry for the first time on this channel. If you expect me to speed up, I think it's going to be a little tough. I'm pretty sure that you must have learnt it, sweetheart, but I'll have to attend to everybody, yeah? And I don't think speeding up is going to be the solution, yeah? So, be with me, everyone. We'll finish it, don't worry. Okay, now let's talk about the melting point, okay? Now, melting point, how does it look like? How does it look like? It looks like the, you know, 3 series of the Himalayas, isn't it? Yeah? It looks like the 3 series of Himalayas. Now, one thing that you have to notice is, everybody, this W, tungsten. Tungsten has the highest melting point. Any idea why? Any idea why? Now, take a look at one thing. You see that how, you know, this is increasing, right? It starts here, then it is increasing, and then it decreases. Why does it increase and then decrease? Why does it increase first and then it decreases? Because first what happens, the unpaired electrons, yes, the number of unpaired electrons keep increasing, and then it decreases again, okay, and then it decreases again. So that is why you get to see this Everest, this Himalaya series that you get to see, okay, you get to see this Himalaya series. Also, you get to see stronger it's the melting point, yes. I'm so sorry, Nishant. I'll try to look here when I talk, okay? I'll try to look this side when I talk. I'm sorry. Yes. Yes, Adil, absolutely right. More is the unpaired electron, more is the melting point. Absolutely right, okay? Higher is the melting point. Also, if the metallic bonding is stronger, okay? If the metallic, not get this melting point. Harshit, you are not getting it? Harshit, what is it that you are not understanding? Tell me. So Harshit, I'm showing you the melting point with this graph. Okay? Harshit, take a look at this. Do you see this graph? Now in this graph, you see that from hafnium to Ta to W, right? Yes? It increases. Why does it increase? Because the unpaired electrons increase. Now, after some time, the unpaired electrons will also decrease, no? If you remember this, my dear student, take a look at this. Take a look at this. See what will happen. The unpaired electron will obviously increase like this. Then it again decreases, no? Why won't it decrease, my dear student? The unpaired electrons are decreasing, right? Yes, it is again going forward to fully filled orbitals. Yes, it is going for fully filled d orbitals, fully filled orbitals. So that means the number of unpaired electrons is decreasing, and that is why the melting point also decreases. Understood, Harshit? Is this clear now? Is this clear? Yes? This we understood, everybody? Yeah? Or stronger is the metallic bond. If the metallic bond is stronger, then also we see that the melting point increases. Yes, the melting point increases. Why Mn is less than Fe? You tell me. You tell me. Why Mn is less than Fe? Think about it. Think about it. Why is Mn less than Fe? Think. Does anybody know this answer? I want to know it from you. But remember this, in every series you have chromium, you have molybdenum and you have tungsten. Okay, these three have the very good. Absolutely right, Nishant and Krishna. Yes. Why is it less? Varshini, did you find your answer? Did you find your answer? Yes, because Mn has less unpaired electrons, okay? Because Mn has less unpaired electron. What is the electronic configuration of Mn? What is the electronic configuration of Mn? What is it? We just spoke about it, no? It is going to be 3d5 4s2, isn't it? Yes, we saw it, no? We saw it, right? See, what is Mn? Mn is going to be 3d5 4s2. That's why, okay? Alright? Yes. Chalo. Moving on, everybody. So, melting point is clear, everyone? Melting point is clear? Yes? Melting point is clear? Clear, everyone? Or no? So, chromium, molybdenum and tungsten, they have the D5 configuration and they have the highest melting point, okay? Alright? Vasant, you are going somewhere else only. No. We are not going to all of that. Yes, we are not going to all of that. Stay here with us. Chalo. Now let's talk about the exceptions, okay? Let's talk about the let's talk about the exceptions. Now we see that Mn and Tc, they also have D5 configuration, but they have low melting points. Now somebody said that, ma'am, it has 5. Very good, KV Santosh. I was coming to it. I said the first answer wrong. Yes, I said the first answer wrong. It is definitely not less unpaired electron, okay? It is definitely not less unpaired electron. Both of them has, say, D5 and D5. Chromium also has 3D5 4s1, whereas Mn has 3D5 4s2. Only one less. You know why? The exception is because of metallic bonding. Yes, it has weak metallic bonding. That is why. Now will you all remember it? Now everybody will remember it that first ma'am said it wrong. Second, next time she already explained it. Weak bonding, not for unpaired electron. The reason is weak bonding. Remember this, everybody. Yes. Both of them have 3d5. Only one unpaired electron less. No. Yes. For chromium it is what? 3d5 4s1. But for Mn it is 3d5 4s2. Only one less. Why should it be so much? Why should the difference be so much? See how twin it's coming down. Why should it be so much? It doesn't have to be so much, right? Only one unpaired electron less. Then why is it happening? Because of weak metallic bonding. Now do we understand this, everybody? Is this clear? Okay, is this clear, everybody? Now we come to enthalpy of atomization. From here also we kind of see not Himalaya basically, this is like the Alps of Switzerland, isn't it? This is like the Alps of Switzerland. It's not very steep, but this is how the graph looks like. Yes, this is how the graph looks like. Now we see here in case of enthalpy of atomization, we see that 3D is less than 4D and 4D is less than 5D. Yes, 3D is less than 4D and then 4D is less than 5D. So that means 5D has the highest enthalpy of atomization. Why? Because again here due to more metal-metal bonding compounds in compounds of heavy transition. Okay, now tell me something. Why do we have more metal-metal bonding on 5D? Why do we have more metal-metal bonding in 5D, everybody? Any idea? You know the answer. Already spoken about it in periodic properties and periodic exception. Yes, Adil, please tell me. Why? Why do we have more metal-metal bonding in compounds of heavy transition metals? Because more electrons are available. And you know that poor shielding effect? There is poor shielding effect, yes? Because of poor shielding effect, the 5D is, yeah, absolutely, absolutely everybody, yes. Because of the 5D being there, they are very poorly shielded. So obviously the electrons are like, coming inside, they are getting the pull of the nuclear charge, and not only them, the other metals are also like, hey, that nuclear is calling us, so let's go. Right? They're all going to participate. Many electrons will participate, and hence even stronger metal-metal bonding. So that is why enthalpy of atomization increases in 5D. Now do we understand this? Yes. Now do we understand this? Again, Ishita, okay, nuclear charge. Let's come to this. Let's come to the variation in atomic size. We will understand this. Okay, let's try this, everybody. Now see variation in atomic size. What happens to the atomic size? Do you see? What happens to the atomic size? Again, we see that for 3D is lesser than 4D, and then 4D and 5D are almost equal. 4D and 5D are almost equal. IIT JEE NEET preparation, we will come to it. Don't worry, I'll explain it to you again. Okay, I will explain it to you again. Now this is due to lanthanoid contraction. Why? Why does this happen? Why does 4D and 5D have almost equal sizes? Why does 4D and 5D have equal sizes? It's written lanthanoid contraction, but how many of you understand lanthanoid contraction? Does any of you understand? How many of you understand lanthanoid contraction? It's very easy, basically. It's very easy. Again, do you remember that I told you during periodic properties and periodic exception, I had told you clearly that if you learn the shielding effect, that's the godfather of inorganic chemistry. You learn shielding effect, you get to answer everything. Learn shielding effect, you get to answer everything. So this is the answer. Now not only d orbitals, now here there are going to be, yes, there are going to be what? F electrons as well, and we know that the F orbital is even a poor shielder. The F orbitals are going to be even a worse shielder, right? It's basically like having those string curtains. Have you seen in some people's houses? In some people's houses, you must have seen that, they don't separate the dining and the living room very well. They don't separate the dining and the living room. What they do is they put those string curtains or those light curtains. But you can actually see who is sitting there and what they are doing. Haven't you seen that? You can easily see, right? Through a string curtain, you can easily see. So imagine those those F orbitals to be like string curtains, right? So the nucleus can actually see the electron, and the nucleus is like, hey, where are you trying to go, bro? Come here. The nucleus will call the electrons. Yes. And because of that, because of this F, I have showed you, remember? Okay, one more time I'll explain you this. Shielding effect. Everybody, forget about lanthanoid contraction. First learn what is shielding effect. Imagine there is an accident that has happened, okay? There is an accident that has happened. And you are going in your school bus. Now, if there are too many people who are surrounding the accident, even if you do this and all, you will still not be able to see, what the accident is about. Some people will come and say, hey, dog got crashed, yeah. No. Some 2 donkeys got crashed. That's the accident about, Then one person will come and say, you know what? One donkey got, banged on this thing, yeah. Banged on the car only, yeah. Right? These things people will come and tell. But imagine the accident has happened and no one is there. Not too many people are there, okay? Not too many people are there. So what will happen? Then they will be easily able to see it, right? So F orbitals are pretty much like that. Royal Sudha, don't do this, no bacha. You might know the point. What is this? Don't drag no point on come to point. You can see that some people do not know, no? Some students don't do this. You might know very good. Yeah, you might know very good. But don't do this with other students, okay? Don't do this with other students. No. You don't like it, you can speed it up later and watch it. I'm trying to explain it for the first time. I can't do this, okay? I'm going to teach you with the utmost sincerity that I have. I can't do this. Plus, you're going for really competitive exams. So, please don't do this. Anyway, alright. So, yeah, now if there are less people, you can actually easily observe what is going on, isn't it? So, the same way, imagine the F orbitals are also like those, 2-3 people. Just 2-3 people hanging around there. But you can actually see, right? And now you know the actual accident, like what happened. So the same way, the f orbitals, they are poor shielders. They cannot shield, and that is why the electron, the nucleus can see that, oh, there are electrons that are revolving around like this. So they will catch hold of the electron and they will not let you go. Yes, and because they catch hold of the electron and they pull them, so what happens? The size goes, the size decreases, and that, my dear student, is your lanthanoid contraction. The presence of the f orbitals is going to be such a bad shielder that all of them will be pulled, and that is why the size decreases. Yes, so now do you understand what is the result of shielding effect? Yes, this is your screening or shielding effect, as we like to call it. So if you remember this, you can pretty much answer each and everything. Yeah, is this clear? Lanthanoid contraction clear, everyone? Yes. Overall decrease in size, absolutely, yes. So overall the size decreases. Got it, everyone? Completely understood, everybody? Any doubt regarding lanthanoid contraction now? Any doubt regarding lanthanoid contraction? This is all clear? Where should I move? See, you can see it. Atomic radii of zirconium and hafnium, 160 picometer, 159 picometer. Not much different. Yes, not much different. Varshini, why is there a final increase in curve? Because as the number of electrons increases, you also understand that sometimes the nuclear charge also increases, right? Little by little, more and more number of protons are also there, isn't it? So, nuclear charge and screening effect, sometimes they try to be equal, and that time the size try to increases a little bit, and you know that, right? Anyway, going that side, the what do you call it? The noble gases, they have the highest size. Why Royal Sudha? Now you want a simple word for lanthanoid contraction. All this time you are like, ma'am, fast enough. Huh? Lanthanoid contraction, basically remember it as that string curtain, okay? Remember it as string curtain. The string curtains, they do not really screen anything, right? You can absolutely see the other side of the room. So remember lanthanoid contraction as the string curtains. It will be very easy for you to remember in the exam also, okay? Chalo, just kidding, Royal, just kidding, it's fine. Royal Sudha, no problem, it's fine. You just told me your opinion, absolutely fine with it. Chalo. Alright, now moving on, let's talk about ionization enthalpy. Does everybody remember what is ionization enthalpy? What was ionization enthalpy? The energy required to take one electron out. And we all know that, the first ionization enthalpy is lesser. The second one is even higher. Remember, what example did I give you? See, one time if I am angry on the YouTube channel, then all my students will get angry. They are like, this teacher is not nice. This teacher only gets angry. The next time, do you think I will have the guts to be angry in the class? I'll be like, no, Baba, I'm a teacher. My students are my greatest asset. If I'm angry in my class, then what will happen to me? I will not be a teacher anymore. Same thing. So once you take away the electron, the second time the atoms are like, let him come, let him give energy, we will see what happens, right? They will do that. So the second time it will be really hard. Second ionization enthalpy will be higher. The third one will be even more higher. Yes? Are you understanding? So exactly. The same thing again we see. The same thing again we see here is that 3D is less, 4D is even less, and 5D is the greatest. Okay? Why? Why is that? Let's understand. Again, due to the poor shielding effect. See, poor shielding effect. Okay. Again, coming back to the example. Now, tell me something. In my house, let's say I have the screen curtains. Okay. I have the screen curtains. I have the screen curtains even on my main door and the main window. Now, if any Swiggy or Zomato wala they come, don't you think I'll be able to see them? I'll be able to see them. Huh? Even in the evening when it is dark outside, that time also I'm keeping the string curtains only open. Okay, I am still looking through the window. Let them come. If there is a thief or something in my area, if they come, and don't you think I can see through the screen curtain? I can. Poor shielding effect, I can see. Do you think now they will have the guts to come and take my things away? See, poor shielding effect. The F1s, because of the F orbitals, the shielding effect is so poor that the nucleus can see everything. Now nobody has the guts. Nobody is going to give the energy to take out electrons, right? It is going to be even more. So do you understand how poor shielding effect of 4f electrons in 5d series and increased nuclear charges increases the enthalpies also? That's it. Easy. Easy, right? Everyone? Now we come to oxidation state. Somebody asked me about how to remember the oxidation state. You want to see the table? You will see the table and you will be able to like, this is so easy, ma'am. So easy. Want to check it out? See. See. Can you see? So it starts with +3, ends with +2. Okay? In between you have 2, 3, 4, 2, 3, 4, 5, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7, 2, 3, 4 and no 5 here, 6, 2, 3, 4, 2, 3, 4 +1, +2 and 2. Okay. Now everybody, yes, now everyone, if you just make this table on your notebook, practice twice, I promise you will be able to remember it. Practice twice and I promise you will be remembered it. Okay, so black caps, you are right. Yes, the maximum oxidation state is +8, but what is visible is +7. Okay, what is mostly visible is +7, and manganese has the maximum oxidation states. Okay, no doubt, you are right, absolutely right. The maximum has to be +8, but what is visible is +7. Now, why manganese has so many oxidation state, everyone? Hi Ravi Kumar, yes, I do remember you, my dear. I do remember you. You come to this channel only, right? I think I've seen you. Now tell me. Ma'am, Hindi mein, Zeus 80, I'm so sorry. This is an English channel and I have to teach you in English. So if you want to watch it in Hindi, I request you please go and watch Mohit Ryan sir's video. He teaches you in the Vedantu JEE channel and he'll be teaching you in Hindi, okay? Please go and watch his sessions. Yeah. Somebody tell me, why does it have the maximum oxidation state? Yes, absolutely. Anita, well done. Yes, see? Why does it have? Oh, okay. Now, tell me something. Okay, one second. Everyone. Nishan, wait. You know Telugu language? No. Why are people asking me for Telugu? Hey, this is an English channel, no? I'm sorry, I do not know Telugu or Tamil or Malayalam or Kannada. Kannada I know a little bit, but it's only to fight with the auto walas in Bangalore, but not more than that. I'm sorry, I'm actually a Bengali and it's a little tough for me to learn the South Indian languages because it's really a lot different from the languages that that I speak. I know a little bit of Bhojpuri, yeah. So I haven't been really able to learn the southern Indian languages, but I'll try my best. Maybe this is the beginning and I'll learn from you all. Okay, all right everybody, coming back to it. Now, why do they show such a variable oxidation state? We have seen it in S block, we have seen it in P block. It was very easy, right? It was very easy for us to predict. We could just look at the group and we could tell that this is the oxidation state. Look and we can say this is the oxidation state, but right here it is variable. Why? Once again, because the n-1 and the ns orbitals, yes, the energies are so similar that they can just jump. And that is why we have variable oxidation states. Okay, we have variable oxidation state. Will this be? Yeah, it will be available. Are we understanding, everybody? Now, you know what? These D block elements, they also have catalytic property. What is catalytic property? I'll tell you what is catalytic property. Tell me something, yeah. So, everybody, imagine that I'm teaching very nicely, okay? And I don't want to be angry, of course. I mean, which teacher wants to get angry? None of the teachers wants to get angry, right? Because being angry is definitely not a good thing for us, right? But imagine I'm teaching very nicely and I'm like, full in mood. I'm like, emotionally flowing and I'm like teaching. But then there are some students, I won't even say students, but there are some people who will come probably and they'll start abusing. They'll be like, ma'am, you're ignoring, ma'am, you're ignoring, ma'am, you're ignoring, ma'am, you're ignoring, ma'am, you're ignoring. But I'm like, hey bro, I'm teaching, why are you not listening? But they are not listening to me. They're continuously writing, I'm not ignoring. Now, the process of a teacher getting angry was actually very slow. The teacher was not getting angry. The teacher was nicely teaching, right? The teacher was nicely teaching and everybody was understanding also. There was no way the teacher was getting angry, but then there were those, people who were like, ma'am, You are ignoring. Ma'am, why are you ignoring? Ma'am, why are you not taking your name? Ma'am, why are you ignoring? Ma'am, why are you ignoring? Why are you ignoring? But hey, the teacher was teaching. The teacher was not ignoring. But what did he do? This fastened up. This fastened up the process of teacher getting angry. Yes. And that, my dear student, is your catalytic property. Fastening up something. Yeah, sure. Allah Ishwar, please. No problem. Go ahead. Yes. Will you teach organic? No plan as of now, but we will see. If Wasim sir has too much of work and he's not able to manage, then I will step in. Otherwise, I'm happy with inorganic right now. I like inorganic. Absolutely right. So what it does is, a catalytic property means that it fastens up the process. It fastens up the process and reduces the energy barrier. By any chance, if something is not able to reach the energy that it wants, what it will do is, it will reduce the energy barrier, and that way it fastens up the process. Okay. Now, why is it used for catalytic property? Because obviously it has variable oxidation state, right? It has variable oxidation state. Yes, correct. There are Shanmukha. Focus here. You will get to know about all of these. Also, they have large surface areas. Okay. They have large surface area, and you know, the whole chapter that we read, ability to form complexes, coordination compounds, complexes. Haven't we read about all of them? We have, right? So that is why they are used for catalytic property. You want to see an example? Take a look at Haber's process. See, iron is used as a catalyst. Yes, iron is used as a catalyst. And why is it used? And what is it? Iron is also a transition element, isn't it? It's a D block element, isn't it? So see how it is used in catalytic property. Got it? Another example, contact process. See, even in contact process, remember V2O5. Somebody even asked me in the chat box, ma'am, what is V2O5? And I told you, vanadium pentoxide. See, vanadium pentoxide. It is a catalyst. Yes, it is a catalyst. Are you seeing it? Yes, are you seeing it? Everyone, that's it is. Yes. So it is used for catalytic properties. Now let's talk about magnetic properties, or if you want, I can stop here and maybe take it the next time, because to be very honest, I am also tired. So can we stop here and take the next session? Till here it is fine. Then we can do the magnetic properties, we can do the formation of colored compounds, potassium dichromate is left, potassium permanganate is left. We also have to study the actinoid and the lanthanoid series a little bit more. Is this okay with you all? It's already 9:35 and I'm kind of tired. I don't want everything to go above your head. This much have you everybody understood? This much have you all understood? When we will do? I have a class on Friday. No, Friday we will complete it. Then Saturday I will do the questions. Saturday we will do the important questions. Is that okay? Harshita, I am not teaching you physical chemistry, Baba. I think I'll not be the right person to teach you, right person to tell you about tips for physical chemistry right now, as I have not taught. Okay. Contact process. Zahara, you forgot. Contact process was preparation of sulfuric acid. Isn't it? How many of you remember that? I think I've taught you. Where was contact process used? Contact process is used to prepare sulfuric acid. And remember, what did we do? We took sulfur dioxide and we had to come to sulfuric acid. So sulfur dioxide, oxygen. Remember, this is what I showed you. Sulfur dioxide, what do you get? Sulfur trioxide. You take sulfur trioxide, then what will you do? You will take sulfuric acid. You will get oleum. Then from oleum, again what do you have to do? You have to add some water and you will get sulfuric acid. That's it. That was the one. Chalo. Alright, yes, so I think today let's finish it here. In the next session, I'll be taking it from magnetic properties, okay? This video enough to cover D and F block? Yes, DJ Computer, not only this, I'll be taking another session of this and then we will complete it, okay? Do a video on surface chemistry. Sure, bacha look, see I have just started with inorganic. I will go where you want me to, but give me some time, okay? Give me some time. Why Fe can exhibit, you tell me, movie, okay. Okay, last question. Why can iron show you Fe2 plus and Fe3 plus? Question solving session Saturday. Saturday we will do question solving session, okay? Friday we will finish this D and F block completely, we will finish it. Then Saturday we will do D and F block question solving session. Pakka question solving session, okay? Yes. Okay, tell me everybody. There is a question that I found out. Yes, somebody has asked me. Yes, why can iron show you +2 and +3 oxidation state? Tell. Tell. In fact, I'll tell you what. I have another question. That I wrote it here somewhere, I think. Why can, I'll give you one more question. No, I'll give you one more question. Who was it? Let me see. Who was it? Somebody else was here. Wait. Where did you go? I forgot his or her name. I forgot your name. Who was it? Movie Hub Rocking Telugu. Yes. Movie Hub Rocking Telugu. I'll give you one more question. You tell me, why is it that iron has +3 oxidation state, which is more stable? Why do we mostly see +3 oxidation state and not +2 oxidation state? +2 oxidation state is seen a little less. Why +3 is seen more? You tell me. Any idea? Very good, Royal Sudha. Well done. That's the answer that I was expecting. Very good. So what is this thing for iron? What is the atomic number of iron? 26, everyone? Yes. Where should I write it? Chalo, I'll write it down here only, okay? I'll write it down here. Iron has 26. Yes. So 26, that means what will it be? It will be what? 26 will be 3d6 4s2. Yes. 3d6 4s2. 3d6 4s2. Now if it gives away 2 electrons, then this is what? 3d6. But if it gives away 3 electrons, 3d5. Half filled is more stable. 3 types are more stable. d0, d5, d10, isn't it? So this is half filled. Either it is vacant, either it is half filled, or it is full filled. And obviously half filled will be stable. So that is why it shows +3 to be more stable. Alright, with this everybody, this is the end of today's session. Thank you so much. If you want to stay connected with me, and if you want to talk to me, and if you want to know about what I do when I'm not taking classes and all of these, then don't forget to follow me on my Instagram account, which is Nabamita_Nobita. Okay, Nabamita_Nobita. That's my Instagram handle. If you want to follow me, I'll see you there. And is that so, Rahul? We will talk about it. Don't worry. If there is any announcement, it will come on this channel. Don't worry about it. Thank you, Sachin. Thank you so much, everybody. Lots of love. I shall see you soon. I'm kind of tired. Otherwise, I would have completed it. But if you look at my eyes, like I'm literally sleepy right now. Okay. So, Tara, bye-bye. See you all, everyone. Do come for the Friday session. Friday also same time, 8:30. Okay. Monday, Friday, 8:30. And Saturdays, I take it at 5 p.m. Okay, Saturday 5 p.m. Alright, 5 p.m. on Saturdays. So I'll see you. I'll put it up on Telegram also. Chal. See ya, guys. Bye-bye. Next class Friday 8:30. Friday 8:30. I'll see you. Be there. Okay. Chal. See ya. Okay, I can't. I'm not able.